Have you ever dreamed of traveling to another planet? Not just sending a robot, but packing your own bags and blasting off to Mars? Imagine looking out the window and seeing the red planet growing larger, knowing you're about to set foot on a world no human has ever walked before. For generations, this has been the stuff of science fiction, but today, it's closer to reality than ever before. For decades, this has been the ultimate goal for space explorers, but the biggest hurdle is the journey itself. Mars isn't just far away, it's a moving target, orbiting the sun at a different speed than Earth. Every mission window is a race against time, distance, and the harsh realities of deep space. The challenges are immense: cosmic radiation, isolation, and the sheer length of the trip. Getting to Mars with current rockets takes 7 to 9 months, a long, risky trip in a tiny metal can. Astronauts would be confined to a cramped spacecraft, exposed to dangerous radiation, and the psychological strain of months in deep space. The longer the journey, the greater the risk of something going wrong, from equipment failures to health emergencies. But what if we could cut that travel time in half? Imagine reaching Mars in just 3 or 4 months instead of nearly a year. Shorter trips mean less exposure to radiation, fewer supplies needed, and a much higher chance of mission success. Suddenly, Mars doesn't seem quite so distant. Enter nuclear thermal propulsion, a technology twice as efficient as today's rockets. Instead of burning chemical fuel, these engines use a nuclear reactor to superheat hydrogen, blasting it out the back at incredible speeds. This means more thrust, less fuel, and the ability to travel farther and faster than ever before. After decades on the drawing board, NASA is finally building a real nuclear rocket engine, Draco. This project, a partnership with DARPA, aims to test a nuclear-powered rocket in space by the end of the decade. If successful, Draco could revolutionize how we explore the solar system, making crewed missions to Mars and beyond a real possibility. This story began in the first space race when nuclear rockets were seen as the future of space travel. But political setbacks, budget cuts, and safety concerns shelved the technology for decades. The NERVA program, once poised to change everything, was cancelled before it could fly. Now, with new tech and a renewed passion for Mars, the dream is back. Advances in materials, safety, and engineering have made nuclear propulsion more practical and safer than ever. Scientists and engineers are working around the clock, determined to make the next giant leap for humanity. In this chapter, we'll explore the fascinating history of nuclear rockets, the cutting-edge technology behind Draco, and what this means for the future of space travel. We'll look at the challenges, the breakthroughs, and the people making it all happen. The future of space exploration is getting a nuclear-powered upgrade. With Draco and nuclear propulsion, Mars is closer than ever, and the next era of human spaceflight is about to begin. Let's jump back to the 1960s, a time when the world was gripped by the promise of atomic power and the thrill of the space race. The United States and the Soviet Union were locked in a fierce competition, not just for dominance on Earth, but for the future of humanity in space. The air was thick with ambition, and every new scientific breakthrough seemed to bring the impossible within reach. It was an era defined by bold dreams, and even bolder engineering. In this climate of innovation, NASA and the Atomic Energy Commission joined forces to launch Project NERVA, short for Nuclear Engine for Rocket Vehicle Application. Their goal was nothing less than revolutionary: to build a rocket engine powered not by chemical combustion, but by the raw energy of a nuclear reactor. This partnership brought together some of the brightest minds in physics, engineering, and space exploration, all working toward a common vision of pushing humanity further than ever before. Unlike traditional rockets that burned fuel and oxidizer, the NERVA engine used a compact nuclear reactor to superheat liquid hydrogen. The hydrogen, once heated to thousands of degrees, would expand rapidly and shoot out of the rocket nozzle, creating immense thrust. This method promised far greater efficiency than any chemical rocket, potentially cutting travel times to distant planets in half. The science was cutting edge, and the possibilities seemed endless. Between 1955 and 1972, a series of NERVA engines were painstakingly built and tested in the Nevada desert. These tests proved that the concept worked, not just on paper, but in the real world. Engineers watched as the engines roared to life, their nuclear cores glowing with the promise of a new era in space travel. Each successful test brought humanity one step closer to the stars. The excitement was palpable. There was serious discussion about using Nerva engines to establish permanent moon bases, and even to send the first humans to Mars. NASA planners and engineers began to imagine missions that would have been impossible with conventional rockets, missions that could carry larger crews, more equipment, and open up the solar system to human exploration. With Nerva, the Red Planet was no longer just a distant fantasy. Teams of scientists and engineers were actively designing spacecraft and mission profiles that could make a crewed journey to Mars a reality. Blueprints and models filled NASA labs, and the sense of possibility was electric. The dream of interplanetary travel felt closer than ever before. The power and efficiency of Nerva meant that astronauts could travel farther, faster, and with more supplies than ever imagined. Missions could be safer and more ambitious, with the ability to carry heavier payloads and provide better life support for crews on long-duration journeys. The technology promised to unlock the solar system for human exploration. For a brief, shining moment, it truly seemed like humanity was on the verge of becoming a multi-planetary species. The optimism of the era was infectious. Scientists, politicians, and the public alike believed that the future would be shaped by nuclear-powered rockets and bold missions to other worlds. The key to deep space exploration was quite literally in our hands. The Nerva engine represented the cutting edge of human ingenuity, a symbol of what could be achieved when science and imagination worked together. But despite all the promise, the dream was short-lived. Budget cuts, shifting political priorities, and public fears about nuclear technology brought Project Nerva to a halt. The test stands fell silent, and the vision of nuclear-powered journeys to Mars faded into history, leaving behind only the echoes of what might have been. If Nerva worked, why aren't we using nuclear rockets now? The answer: shifting priorities and politics. After Apollo 11, public excitement faded and budgets shrank. The Vietnam War and domestic needs made expensive Mars missions seem out of reach. With no clear mission, Nerva lost its purpose and funding. Safety concerns about launching nuclear reactors also played a role. In 1972, Nerva was cancelled, and the dream went dormant. The technology worked, but its time hadn't come. The world had other problems to solve. The dream waited for a new generation to revive it. Fast forward 50 years, the dream of Mars is back. NASA's Artemis program is paving the way, but to go further, we need better engines. Enter Draco demonstration rocket for agile cislunar operations. Developed by NASA and DARPA, Draco is the modern successor to Nerva, using new materials and smarter designs. The goal: launch Draco in 2027 and fire up its nuclear engine in space for the first time. This test will be a historic leap, moving nuclear propulsion from theory to reality. Draco could make Mars missions routine, not rare. The sleeping giant of nuclear propulsion is finally awake. Its name is Draco. How does Draco work? Think of it as a supercharged space kettle. Instead of a metal coil, it uses a nuclear reactor to heat liquid hydrogen. The reactor's special uranium fuel, HALEU, gets incredibly hot, turning the hydrogen into gas in a split second. This superheated gas blasts out the nozzle at up to 10,000 meters per second, pushing the spacecraft forward. Advanced ceramics and alloys keep the engine from melting under extreme heat and radiation. These materials didn't exist in Nerva's day. Draco's combination of safer fuel and stronger materials makes it a true 21st century machine. It's a masterpiece of engineering and materials science. Why is Draco such a big deal? Let's compare it to today's chemical rockets. Chemical rockets are like family cars, reliable but limited. Draco is the race car, twice as efficient, with a specific impulse of 900 seconds or more. This means you can get to Mars in 4 to 5 months instead of 9, or carry more cargo with less fuel. The secret is the reactor's ability to heat hydrogen far hotter than any chemical flame. Faster exhaust means more thrust for the same propellant. It's like firing a bullet instead of throwing a baseball. Draco is the engine that fires bullets. More speed, more efficiency, more possibilities. It's a revolution in space travel. Getting to Mars faster isn't just about speed, it's about safety. Deep space is filled with dangerous radiation that can harm astronauts' health. The longer the trip, the higher the risk. Cutting travel time in half means less radiation exposure and fewer long-term health risks. It also means less need for heavy shielding, making the spacecraft lighter. Shorter trips reduce muscle loss, bone weakening, and mental strain. Faster rockets give mission planners more flexibility and options for emergencies. More power and speed means safer, more successful missions. Draco isn't just about going fast, it's about protecting the crew. Speed is safety in deep space. When it comes to the future of space exploration, two names stand out: Draco and SpaceX's Starship. But how do these two technological marvels stack up against each other? Are they competitors, or is there a bigger story at play? The truth is, they're not rivals at all, they're more like partners in a grand cosmic adventure. Each brings unique strengths to the table, and together they could redefine what's possible for humanity in space. Starship is the heavyweight lifter of the space world, massive, fully reusable, and engineered to carry enormous payloads and crews into orbit and beyond. Its sheer size and power are unmatched, making it the backbone for launching habitats, supplies, and even entire missions. Starship's strategy is all about scale and affordability. By launching multiple ships and refueling them in orbit, it can send larger missions farther than ever before, opening the door to ambitious projects like lunar bases and Mars colonies. Draco, on the other hand, is a game-changer for deep space travel. Powered by nuclear thermal propulsion, it's designed for efficiency and speed, slashing travel times across the solar system and making distant destinations more accessible. Think of it this way: if Starship is the cargo truck hauling everything out of Earth's gravity well, Draco is the bullet train that races across the vast distances between planets, getting astronauts and cargo to their destinations faster and with less fuel. Starship's job is to get missions off the ground, breaking through Earth's atmosphere with power and reliability. Once in space, Draco takes over, propelling spacecraft across the solar system with unprecedented speed and efficiency. Imagine a future where Starship assembles a nuclear-powered Draco ship in orbit, combining the best of both worlds: raw lifting power and rapid interplanetary travel. With Starship handling the heavy lifting and Draco providing the speed, missions to Mars and beyond could become routine, safe, and even affordable for future generations. Working together, these two titans could make regular Mars missions a reality, turning science fiction into everyday science fact. Two champions, united by a single vision, to explore the cosmos and push the boundaries of human achievement. In the end, the future of space travel isn't about competition, it's about collaboration, innovation, and reaching for the stars together. The nuclear rocket's journey is reaching a turning point. In 2027, Draco will fire its engine in space for the first time, a moment 60 years in the making. If successful, it will prove nuclear propulsion is ready for real missions. Next, bigger engines, crewed Mars missions, and new spacecraft designed for long journeys. Draco's success could shrink Mars trips to 4 months and open the outer solar system to exploration. The dream that began with Nerva is closer than ever. Draco is more than hardware, it's a symbol of human persistence. A good idea never dies, it just waits for its time. Soon, a nuclear rocket may light our way to the stars.